So we are now moving on to the slightly trickier logical operators. Not much worse, but these ones, well, this next one can be a little bit confusing, but I'll say more about it even in a second. So this is if then. Also, I will commonly call it implies, and denoted by a double struck arrow. The book denotes it by a single arrow. These are all different ways of saying it. And one of the reasons this can be confusing is that there is a million ways to write it. So, for example, if P then Q, this is the headline way. P implies Q. This is this way. Of course, you can use the double or single arrow. It implies Q, but there's also lots of more exotic things like, P, therefore Q. Or even wilder things like for Q to be true, it is sufficient. Oh my gosh. Sufficient that P is true, and many, many more. But essentially, it means, all of these mean the same thing, which is that if P is true, then Q is true. But even this truth table is a little bit trickier to write down. So let's take a look at it. So we have P and Q, and P implies Q. And the reason it is tricky Geez, I thought I had that muted. Don't send me notifications. All right, whatever. So the reason this can be tricky is because, so if P is true, then Q is true. It works in this case. So let's call that true. In the second case, if P is true, then Q is true. Q is false, so that does not work. So this is false. But what do you do when P is false, right? This is a little bit stranger to try and interpret this statement. If P is true, then Q is true. What do you do if P is false? And there's actually a name for this. So if P is false, then this proposition is vacuously true. Which is essentially, what that essentially means is that there's nothing to check. So the default is true. Right, so if P is false, let's say we're in this situation, and we try to evaluate the statement. If P is true, that's not a situation that we're worried about. That's not the situation we're in. So there's nothing to check, and let's just say it's true. So in both of these situations, it is true. So this is part of the subtlety of P implies Q, is this thing, but I will have more to say about it in a second, after we finish this last guy. So the last one is if and only if, which is commonly denoted by IFF. So this, not a type. This is just a shorthand for if and only if. And you can also use a double-sided, double-struck arrow, or I think, again, the book uses a single double-sided arrow. And you'll probably see me use this a lot just because that is a lot to type. I mean, okay, if I'm typing, I'll probably say this, but if I'm writing by hand, you know, okay, so I'm going to do it right now. So P, Q, and P if Q. P if and only if Q is how I should read that. And what does this one mean? This one means, this might be the thing that we were asking about and before. So let me get to this question in a second. So this means P and Q have the same truth value. So if P is true, then Q is true. And if P is false, then Q is false. And in the situation that they're different, that is not satisfied. Okay. So let's go back to this if-then, because we are getting a couple of questions about this. Why is it true when P and Q are false? And this seems like an innocent until proven guilty approach. That might be a decent way of thinking about it. Somehow, that's what vacuous truth is kind of getting at, is that if there's nothing explicitly false going on, then let's just say it's true. So it's true in this situation. I think this is what the question was about. It's true in this situation for the same reason over here, that it is vacuously true. If P is false, then nothing else matters, because the whole premise does not apply, right? So if P is false, we're not even asking a question, right? So both of these cases are vacuously true. It doesn't matter. I mean, you can see that it doesn't matter what Q is. This immediately tells you that it's true. Okay. So let's actually return to this implies, or let me make a note. So the order of the propositions doesn't matter for and, or, XOR, and if and only if, right? For all of these ones, it doesn't matter what order you put P and Q in, but implies, or if then, it does matter. So let's talk about this for a second. We have a couple names for these things. So if we have an implication P implies Q, then the converse is Q implies P. The inverse is not P implies not Q. And the contrapositive is not Q implies not P. Quick question. P is false, it is vacuously true, so back up in this situation. If P is false, then P implies Q is vacuously true. That's the same thing as true. There's no, I say that as a clarification of how you conclude that it's true, but being vacuously true just means that it's true. There's no distinction there. Okay, so back to our new words. So the point of giving names to these things is that there are certain relationships between them, and they are different things in general. So in particular, they're not all the same. Although some of them are. So in fact, P implies Q is equivalent. Maybe I'll say more precisely what equivalent means in this situation. I'll say that in a minute, in a later thing. But an implication, P implies Q, is equivalent to its contrapositive. Not Q implies not P. So these are actually equivalent, these two. And you can check that these two are also equivalent. In fact, they are the contrapositives of each other. If you want to unwind what that means, you can probably figure it out. So these two are always the same. These two are always the same. But these two are different, and these two are different. And you should be careful not to confuse them. So let me even write that down. So confusing these is a common mistake. So you should be aware of that. Be careful that you do not prove the converse of the thing instead of the thing, because it is not the same. Why is a thing the same as its contrapositive? That is a good question. It is not obvious. But I think I will leave it as an exercise for you to work it out, and I will just give some examples instead. So exercise. You can write down the truth table for P implies Q, and not Q implies not P. And you will observe they're the same. But let's just give some examples real fast. So x is greater than 3 implies x is greater than 2. This is a proposition, and it is true. Right? If a number is bigger than 3, then certainly it's also bigger than 2. Converse, if x is greater than 2, then x is greater than 3. This is not true, you will find, right? Because, for example, you can take x equals 2.5. It is bigger than 2, but it is not bigger than 3. Not bad. And you can do a similar thing for the inverse. So the inverse, let's remember real fast, means we keep them in the same order, but we put a not in front of each of them. And what does that do in this situation? What does it mean that x is not greater than 3? That means x is less than or equal to 3. And same on this side. If x is not greater than 2, what is the negation of this? Is that x is less than or equal to 2. We keep them in the same order. So this is also false. Same reason. So 2.5 is at most 3, but it is not at most 2. But on the other hand, the contrapositive well, what is the contrapositive? We apply not to both sides, just like we did here, but we also switch the order. So the contrapositive is x less than or equal to 2 implies x less than or equal to 3. And this one actually, again, is true. As we expected from what I said up here. Because if a number is at most 2, then it is also at most 3. Okay, so that is a little introduction to a bunch of different logical operators and a little bit about how to work with them. I want to take a quick break to just check out some things as like a little bit of motivation, some places that you see them in nature. So one of the things that I was saying as motivation for this is that these basic building blocks of logic form essentially the basis of any mathematical reasoning. So let's take a quick peek at, so here is Sanders' thesis that he is in the process of writing. Here is my part of a little draft of it. And I just want to point out that you can find these things all over the place. Like lemma 6.1.7 that we're looking at right now. Maybe you don't understand what the precise things mean, but you can see that it has this basic form. It is saying if something and something else, then third thing. So it's basically of this basic form, if P and Q, then R. So this is how all of mathematical reasoning is basically set up. That's a nice little example. And then you will also commonly see these things popping up very explicitly in computer science. So a lot of the way that computer programs work are basically they are following your directions using these basic logical commands. So here is some coding stuff that I've been messing around with. If you don't know about Google Colab, it's a great, super cool place to, go write code on the web without needing to have anything on your computer. Really nice tool. Check it out if you're into coding. But I just wanted to point out, there's tons of statements in here that are like, if something is true, then execute some code. Or even, here's, I'm not doing a good job at this. You have things like, at this line, getting some lag, but hopefully it's fine. You have if P and Q, then you execute this code, and things like, if on this line, if P or Q, then execute some code. So again, just examples of how this kind of basic logical reasoning is going to be pretty fundamental for any kind of mathematics and computer science that you are interested in doing.